Welcome. We are going to do another induction proof here, taken from Discrete Mathematics and its Applications by Kenneth Rosen. I'm using the 7th edition, which means that I am out of chapter 5.1, and this is question 21. The question asks us to prove that 2 to the n is greater than n squared for integers n greater than 4. So n squared is less than 2n for n greater than 4. So we will prove this by induction. Of course, on n. So n is greater than 4 means our base case is for values of n equal to 5. So this is the P5 case. That's where we're starting with this integers. So let's check, see if our base case holds. N squared is 5 squared is 25. 2 to the n is 2 to the 5 is 32. So 25 is indeed less than 32, so the base case holds. Now, let's write out the inductive step. So here we're going to assume that k squared is less than 2 to the k. For k is greater than 4. So this is our induction hypothesis. The IH. So we're assuming this is true, and then showing that it will hold for the k plus 1 case. Now we'll be building inequalities. I've said this in other videos that are looking at induction proofs with inequalities. And I've used the same example, so let me continue. If I want to show that 1 is less than 4, which is an obvious statement, I could build from the left and say, well, I have something that I know to be true based upon some fact. 1 is less than 2. And let's say that I also have by fact that 2 is less than 3. And similarly, 3 is less than 4. Now, if I put all these together, I have this chain of inequalities. And by transitivity, I have 1 is less than 4. So we could proceed that way by looking at the left-hand side and the right-hand side of our inequalities and build, putting them together, and then coming to our necessary conclusion, which is usually how I like to approach this. It's a good way to look at the inequalities and get comfortable with them. This proof is going to be a little different than the previous ones, and we'll get to why that's true in a second. So we want to show, so the induction hypothesis is essentially the PK case. It's just a restatement of k squared is less than 2k as the induction hypothesis. That's what we're assuming to be true. We want to show that the pk plus 1 case is true. And I like to write that out literally, like what it is we're trying to show. So k plus 1 squared is less than 2 to the k plus 1. Put a little question mark above that inequality, because that's not something that we're assuming to be true. That's something that we're showing to be true. This is what we want to be able to conclude based upon our argument. So let's look at the left-hand side. This k plus 1 squared. Of course, if we remember our exponents. Squared means I'm taking that and I'm multiplying it by itself. And I have k squared plus 2k plus 1 by FOIL. You can review multiplying polynomials. I'll put a link above somewhere that will take you to that video if you need to review how to FOIL or how to multiply polynomials. All right, so that's k plus 1 squared is k squared plus 2k plus 1. So now let's look at our induction hypothesis. Why I like to write IH so I can call it back. So the induction hypothesis, we have k squared is less than 2k. Now, k is greater than 4, which means that 2k plus 1 is greater than 0. In other words, 2k plus 1 is going to always be positive. So 2k plus 1 is greater than 0. Now, why do I care about 2k plus 1? Well, I'm going to add 2k plus 1 to both sides of this inequality, to both sides of the induction hypothesis. And the inequality holds. So k squared plus 2k plus 1 is less than 2 to the k plus 2k plus 1. So now we want a particular result here. In other words, I want I want 2k plus 1 to be less than 2k. If this is true, then I can add 2k to both sides of this, and I've created a chain of inequalities that will lead me to the necessary conclusion. So this is what we want. We want this to be true. Now we can just reason through k is greater than 4. We can plug some numbers in, which will be fine. But what I'm going to do, maybe unnecessarily, is to show by induction this is true. Now, perhaps in your class or your professor won't require this. You can just reason through this. I'm going to show by induction that's true. So it's an induction proof within an induction proof. It won't be too bad. So I'm going to put it as a indented aside here. So we're going to proceed the same way. We're going to say the base case is k equals 5. So that's 2, 5 plus 1 equals 11. And 2 to the 5 is equal to 32. So 11 is indeed less than 32. So we're going to assume that 2k plus 1 is less than 2k. And here we want to show that 2k plus 1 is less than 2k plus 1. This is what we want to show. In other words, this is the pk plus 1 case. This is the pk, and this is p5. So this is an aside. Again, you don't necessarily have to do this, but I just want to be a little bit thorough. So the left-hand side, we have 2 times k plus 1, which is equal to 2k plus 2. Now, by induction hypothesis, we're saying that 2k plus 1 is less than 2 to the k. So we can add 2 to both sides. Because 2 obviously is greater than 0, it does not affect the inequality. So 2k plus 1 plus 2 is less than 2k plus 2. So this is 2k plus 2 plus 1. And what is 2k plus 2 to the 1? Well, if I factor out a 2, k, well, I don't need to necessarily do that, do I? This is just 2k plus 1. Because if I have 2 to the 1 and 2 to the k, 2 to the 2 is less than 2k, so I can write that as 2k plus 2 is less than 2 to the k plus 1. So I have my little chain of inequality here. And this, of course, is 2k plus 1, this factorization, plus 1 is less than 2k plus 1, which is what we wanted to show. So it is true that 2k plus 1 is less than 2 to the k. So why did we go through all of that? Well, we're going to take this 2k plus 1 less than 2k, which we know to be true. We're going to add 2k to both sides. 2k is positive. This won't affect the inequality. So 2k plus 2k plus 1 is less than 2k plus 2k. And from the previous left-hand side, we had k plus 1 squared, which was equal to k squared plus 2k plus 1, which we said was less than 2k plus 2k plus 1, which is 2k plus 2k. Just to be thorough, let's explain why 2k plus 2k is equal to k plus 1, 2k plus 1. Again, if you need to review exponents, put the link in the video. So I can factor out a 2k, which leaves me with 1 plus 1, which is just 2, and add the exponents, then that's 2k plus 1. So this is equal to 2k plus 1. So all of that allows us to say that k plus 1 squared is less than 2k plus 1 by this long chain of inequalities. All right, so I did that a little aside here. Again, induction proof within an induction proof. Not entirely necessary. I think it might be safe to assume that 2k plus 1 is less than 2k. And you could add 2k to both. There's definitely a quicker way to go through this, but I wanted to give you the induction with an induction just so I can convince you that that was true. And so that is what we wanted to conclude. Some like QED, I like little boxes, but I've been putting both for absolutely no reason. So that's it. We have proven that 2 to the n is greater than n squared for values of n greater than 4. All right, thank you for watching. Like, subscribe, comment, do all that wonderful stuff, and hope to see you back soon. Thank you.